G'day everybody, welcome to another video. So today we're going to be talking a bit more about AES, and I tell you what, if you ever wanted a difficult topic to tell someone about, this is a pretty good place to start. This is the big bad MixColumns step. This step actually is what I found interesting about the algorithm. This is why I started looking into AES as a whole, because I find the maths of this, the algorithm, it's just bizarre. Anyway, it was going to be one video, but I found that I was kind of rambling and going into a coma at about the hour mark, so I decided to split it into two videos. So today we're going to be looking at the dot product, and next time we'll look at matrix multiplication. So we're talking about the dot product between two Galois fields, and I think the best way to do this is just take it easy. I also want you to note that if you're getting confused or bored halfway through, a lot of what we're going through today just becomes a couple of table lookups. Yeah, so it's really not hard to implement in the end. It's just going to be a few lines of code and a table lookup. Good stuff. Alrighty, so what in the world is a dot product? Well, if you've got yourself a vector, a couple of vectors actually, you can perform this operation between them called the dot product. It's often drawn as just a little dot like that. And what it means is you get each corresponding element, so the 1 and the 12, you multiply them together and you sum up the products. So 1 times 12 plus 2 times 14 plus 3 times 15 plus 4 times 17 will give you the dot product of 153. Okay, so something to be careful of is that, or something to think about is the fact that you don't actually need numbers in your vectors or your lists. All you need is items that have defined for them the addition and the multiplication operators. So usually it's numbers, but so long as you've got multiplication and addition defined for your elements of your lists, you can get the dot product. I don't know if I mentioned it, but they have to have the same number of items. Yeah, otherwise there would be no corresponding element in one of the lists. Okay, so that's what your basic dot product is. But we're dealing here with Galois fields, not numbers. So, like I just said, you don't need to have numbers in your vectors. You can actually do a dot product with anything so long as you've got multiplication and addition defined for those elements. So the Galois field, if you remember, is just a weird way of looking at the bytes in our little state, in our key. If we've got the bytes like this is the bits of a byte. If I just put, oh no, I won't bother. This is binary just here. So this is the 7th bit over here, and you can see that it's set to a 1. So the polynomial that represents will have 1 by x to the 7, or just x to the 7. We've also got a 1 in the 6th position, so we get x to the 6. There's no 1 here in the 5th position, so you'll see down here that there's no x to the 5. But we do have an x to the 4, we've got an x to the 2, and we've got an x to the 1. So this bit sequence just here becomes this polynomial when we imagine it as a Galois field. Likewise, this second bit sequence over here becomes x to the power of 5 plus x to the power of 4 plus x to the 2 plus x to the 1. Nice and easy, so just a little recap there on what a Galois field is. It's just a reimagining of a bit sequence as a polynomial. Okay, now we're going to talk about polynomial multiplication, but it's slightly easier than normal polynomial multiplication when we're dealing with Galois fields, because we're going to be taking the modulus after division by 2. So it's always mod 2. Our answers are never going to have 2x to the 3. It's always going to be 0x to the 3 or 1x to the 3. Yeah. Okay, so when you multiply two polynomials together, and we'll do this in just a second, what you end up with is a term for every pair of terms in the operand polynomials. And you also might remember that x to the power of z multiplied by x to the power of y equals x to the power of z plus y. So the products that we're going to be finding here in our Galois field actually become a series of additions of exponents. And at the end we've also got to do the mod 2 thing. Okay, but let's have a bit of a demo on how this works. I'll just get my pen out. All right, so that's the two polynomials up there from the example just a minute ago. So if we were to multiply these two polynomials, I can't zoom for some reason. It's very annoying. If we were to multiply these two polynomials normally, what we would do is, well, you might start out by saying x to the 7 times x to the 5 gives x to the 12. X to the 7 times x to the 4 gives x to the 11. And then we will do the 7 and the 2, which means x to the 9. You see, so you just plus up the exponents. 7 plus 2 gives you 9. And the last one will be x to the 7 times x to the 1, which gives us x to the 8. And then we would move on to the 6. So x to the 6 times x to the 5 gives us x to the 11. X to the 6 times x to the 4 gives us x to the 10. Yeah, then you would figure out x to the 6 times x to the 2, then x to the 6 times x to the 1. And after you've done all of the 6's, you would move on to x to the 4. So x to the 4 times x to the 5, x to the 4 times x to the 4, etc, etc, etc. After you've done all the 4's, you'd go x squared times x5, x squared times x to the 4, x squared times x to the 2, x squared times x to the 1. And that'll be your next line. And finally, you'd have the x to the 1 times x to the 5 times x to the 4 times x to the 2 times x to the 1. So what you see is that you'll end up with, what is it going to be, like 20 little terms here. Yeah, all of the pairs of elements of these two polynomials. But let's just go through a bit of a quicker way to do this because, well, there is a bit of a faster way to set this out. We don't have to write all of that x to the power of and all of those pluses in between our results. You know, we had a bunch of x to the power ofs and pluses in our results. What we can do is just write it out as a grid. So if I write 1, 2, 4, 6, and 7, the powers of the first polynomial over the side, 1, 2, 4, 6, and 7. And as the columns, we'll write 1, 2, 4, 5. Just like this. So don't do this in exam. If you're doing polynomial multiplication, don't do it like this. You'll probably get marked down. Unless I'm marking. Alright, so now we're going to figure out exactly the same thing, all of the powers that we need in our final result, but we're just going to write it out in a grid. So all we've got to do is add all of these values together. So 1 plus 1 gives us 2, 1 plus 2 gives us 3, 1 plus 4 gives us 5, and 1 plus 5 gives us 6. 2 plus 1 gives us 3, 2 plus 2 gives us 4. You see, I'm just adding the numbers here, the row and the column. Yeah, we're figuring out exactly the same thing as we did before without all the x's and the pluses. 2 plus 4 is 6, 2 plus 5 is 7, 4 plus 1 is 5, 4 plus 2 is 6. What's happened here? There we go. 4 plus 4 is 8, and 4 plus 5 is 9. 6 and 1 is 7, then we've got a bit of 8 happening, and we've got a bit of a 10, and a bit of 11. 7 and 1 is 8, 7 and 2 is 9, 7 and 4 is 11, and 7 and 5 is 12. Okay, so these just here, these numbers represent the powers that we would have gotten if we'd multiplied that polynomial normally. So this 12 just here means x to the power of 12. You'll note that there's only one of those 12s in this grid, so it would mean 1 x to the power of 12, or just x to the power of 12. You see that there's two 11s just here? So if we multiplied this polynomials out, what we'd get is 2x to the 11. Alrighty. There's one 10 just here, so we'd get 1x to the 10. Okay, but if we just... Whoops, what's happened? That doesn't matter. If we just rewind a bit, we're working mod 2 here, so we can't have 2 to the... Get out of here, shear. Swap tools accidentally and went to shear. We can't have 2 by x to the 11. What it is 0 by x to the 11 or 1 by x to the 11. Yeah, we're working mod 2 here. So this 2 is an even number. It actually becomes 0 by x to the 11, which means that in our final polynomial, we actually don't include the 11th bit at all. It's going to become a 0 in our final result. Let's just rewind again and we'll go through the whole shebang. Alrighty, so what we've got to do is figure out if there's an even or an odd number of each bit. So these are actually the bits, positions in our final result. So this 12 just here, there's one of them. So that means that there's 1 in the 12th bit of our final result. The 11, I'll just put a circle around that. The 11s, you'll see there's two 11s, just here like this, which means that in the 11th position, we would have a 2, because there's two of them, but we're working mod 2 here, so that actually becomes a 0. Yeah, so every time there's an even number of one of these, it's going to become a 0. Every time there's an odd number of a particular bit index, it's going to become a 1. I'll just cross out the two 11s because we've got 0 there. All right, so there's 1 10 just here. 1 is an odd number, so we'll put a 1. There's two 9s. 2 is an even number, so we'll put a 0. I start to get really confused and trip over odds and even numbers here. You'd think it was simple. Anyway, there's 1, 2, 3 8s just here. So it means that the 8th bit in our final result will be set to 1. Yeah, like we were saying before, you can't write 3x to the 8 in your final Galois field. You've just got to write 3 mod 2, which is 1. There's two 7s. 2 is an even number, so we'll write a 0. You see what we're building here? We're building another Galois field written out as a bit sequence, which is the result of these two polynomials multiplied together mod 2. All right, moving on to 6s. There's 3 6s. 3 is an even. No, it's not. 3 is an odd number, so we'll write a 1 in our final result. There's 2 5s, so there's a 0, because 2 is even. There's 1 4, so we'll put a 1. There's 2 3s, so we'll put a 0 because 2 is an even number. There's 1 2, so we'll put a 1 there. And you'll see at this point that we haven't got any 1s at all. So there's 0 1s in this list. There's 0 1s. 0 is an even number, so we'll put a 0 there. Likewise, there's no 0s either. So there's 0 0s and there's 0 1s. Which means that we put a 0 in the 0th column as well. And what we have here, like I just said, is a polynomial, or it's a Galois field representation in bits, just like we had before. If we have a look at the slides, just like this here. Yeah, but the bits represent these two polynomials multiplied together and mod 2. All right, so this is bit 0 just here of our final polynomial. This is bit number 1, this is bit number 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so this is bit number 12 over the side. Good stuff. All right, so that's how you multiply polynomials. Let's just move along because we've got another step. Okay, so multiplying two Galois fields could potentially result in a product that doesn't fit into a byte. And that's pretty obvious because the one that we just did doesn't fit into a byte. This right here is, 13 bits long. And a byte only holds 8 bits at most. So this answer just here doesn't fit into a byte. And that's a bit of a problem because we're working with bytes. We're going to want to store our answer in bytes. So if I just copy that and wipe this out and paste it at the top, we're going to go through the next amazing step. The next amazing step is to reduce our answers mod this polynomial. This magic special polynomial just here is specifically chosen so that it will always result, when we divide by this and take the remainder, it will always result in a byte length for our final answer. And it will always result in a unique byte for every input, which is good because we want to reverse this. You know, we're encrypting here, and at some point we may want to decrypt. So you want to be able to reverse the operation. All right, but what we've got to do is have a look at what reduction mod this value actually means. And it's similar. It's similar to long division that you might have learnt in school. I don't know how many people do long division outside of school. Short division is often better, but the algorithm that I'm about to use is similar to long division. So if we just write this polynomial out, what is it? 8, 4, 3, 1, 0. We're going to want to write it out as a bit sequence. Let's have a go. So there's an 8, There's no 7, there's no 6, there's no 5, there's a 4, there's a 3, there's no 2, there's a 1 and a 0. So that is the bit sequence of the polynomial that we just saw before. Yeah, if we write it out as a one of these bit sequences. So what we're going to do now is similar to long division, except instead of subtracting, let's just have a quick recap of long division. If you've got something like 5, 4, 3, right, and you're doing long division, this is just quietly, if you're doing long division, you write a 1 there, and you put a 5 there, and 0, you bring down the 4, there'll be a 4 there, so 0, and then you would say, well, 5 doesn't go into 4, so that'd be a 0, then you subtract and end up with 4 down here, you bring down your 3, and it goes into that 8, it gives us 40 minus, gives us 3. So your answer after long division would be 108, remainder 3. This 3 right here. See, look at that. As it happens, we're not interested in this 108 in what we're doing here in AES. We're only interested in the remainder. So I won't be keeping track of the 108 at the top. I'll just be performing the subtractions and bringing down the digits. Okay, that's what we're doing. That's what we're doing. But we're doing it in binary with these Galois fields. Whenever you subtract one Galois field from another, it's subtraction mod 2, just like the addition that we looked at. And interestingly enough, subtraction mod 2 is actually exactly the same thing as addition mod 2. So what we're really going to be doing here is just XOR, exactly the same as when we were doing addition mod 2. Okay, well what you want to do is shift this magic polynomial as far as it will go to the left of your answer that you're trying to reduce, and then you want to perform XOR. So if we perform XOR, we'll get 1 XOR 1 gives us a 0, 0 XOR 0 gives us a 0, 1 XOR 1 gives us a 1, then we got a 0, then we got a 0, and a 1, and a 1, and a 1, and a 0. And then we've got to bring down these other digits just here on the end. We can't forget those, so I'll put those on the end. 0, 1, 0, 0. Okay, so that's all those values just there. And at this point we've performed one round. So what we've got to figure out now is our answer larger or smaller than the value that we're reducing by? So it's actually smaller. So what you want to do is once again shift this magic polynomial as far as it will go to the left without becoming larger than your result. Okay, so we'll do that. We got 1, 0, 0, 0, 1, 1, 0, 1, 1. Okay, so that's there as far as it will go to the left, and once again we have to perform the subtraction. Incidentally, what we found out up the top here was that if we were doing long division, we would have put a 1 there. Yeah, and here we just had to put a 1 here too. Yeah, it would look something like that. But we're not doing long division. We're doing some XORing. So let's do this next XOR. Just the same as before, a bit of XOR action. Alright, so 1 XOR 1, well that's going to give us a bit of a 0, and then there's going to be a 0 there, 0, this will give us a 1, that'll be a 0, 0, I don't know why my handwriting's gotten so small, that'll be a 0, that'll be a 1, 0, 0, 0. Okay, so that's our answer now. Now we've got to figure out, is that larger or smaller than the value that we're reducing by? Well, I think it's smaller. 1, 0, 0, 0, 1, 1, 0, 1, 1. Aha! It's smaller. So this value here that we're reducing by no longer divides our answer, which means that our answer is currently the remainder after that division. So that right there, 1, 0, 0, 0, 1, 0, 0, 0 is the answer that we're looking for. That number, if we just reverse and say exactly what that is, that number is these two polynomials multiplied together as Galois fields, so mod 2, and reduced mod this polynomial just here. So we're ensured that this value that we get at the end will always fit within a byte, and it does. It fits within a byte, no worries. I'm pretty sure that's not the same answer I got last time, so I must have made a mistake, but I don't know, it doesn't really matter because those two polynomials that we were multiplying together these two, you would never actually do that in AES. As we'll see, this second polynomial here is one of just a select few. But I wanted to go through that because I wanted to show how to reduce mod this polynomial just here. And when you're actually doing AES, the reduction step in encryption just becomes a couple of XORs. So I didn't want to say that we're just XORing with this value just here, because we're not. Yeah, good. Okay, so that's all for multiplication. We will have a big demo at the end. But the other thing that we need when we're computing the dot product, we need addition. So you multiply corresponding elements and then you add all of those products together. So once again, addition in this AES with these Galois fields is addition mod 2, just like we did in the add round key step. In other words, it's XOR. Okay, so what we're basically doing is multiplying values and then reducing them mod that awful little polynomial. But what I want to say is that when you're encrypting with AES, you actually get this special matrix that you multiply by. And this is where the other half to the dot products comes from. And in this second matrix, the values are either 1, 2, or 3, as we'll see in the next video. So multiplication of Galois fields by another Galois field that's equal to 1 is actually the same as not changing your value. Multiplication by the Galois field of 2 gives anything, any one of 256 different values depending on what your input byte is. And it's the same for multiplication by the Galois field of 3. So what we've really got here is 2 lookup tables. We need to pre-compute multiplication by the Galois field of 2 and pre-compute the multiplication by the Galois field of 3. And we can store those values already reduced by that polynomial that we saw a minute ago in a table, in a lookup table, so we don't really have to compute any of it. If you come over here to Rindale MixColumns and you scroll down just a little bit, this will be code examples of how to create the tables, but we're not really interested in that. We've just been through how to do it by hand. If we come down a little bit more, here we go, multiply by 2. So this right here is a lookup table of the answers that you would get if you multiply bytes by the Galois field of 2. If we just copy this over to our code, we're not going to be coding very much today, but we will use this. I'll call it mul2. So in the end, we don't have to worry about any of that stuff that we just went through. We can just use a lookup table, which is, it's pretty handy, but I think it is nice to know where the values in this lookup table came from. So good. Mal, call it mal, and I'll put a apostrophe there. No, it won't. Let's go back to multiply by 3, and we just copy this, copy. And you might be wondering what the heck these tables are for, but we'll have a bit of a look in a minute, because at the end here I've got a great big demonstration. All right, so as a recap, and this is probably going to take half the video. In summary, what we're doing is computing dot products of vectors of Galois fields, because later on, next video, we need to multiply matrices, and that's just a whole bunch of dot products. What it means is multiplying corresponding Galois fields from vectors and summing the products. And we know already that our vectors are going to be multiplied against the Galois fields of 2, 3, 1, and 1. After you multiply corresponding elements, we're reducing modulo this specially selected polynomial just here to make sure that our answer fits into a byte. And once we've reduced the products, we can add them by XORing. Since we're making a dot product here, we want to add all of the products together. And instead of doing normal addition, we want XOR, since we're working with Galois fields and it's mod 2. So for the final example here, what I want to do is just go through by hand how to do the multiplication of this, or the computation of this dot product just here. And this is actually a dot product that you might find in AES, whereas before the multiplication that we did, you wouldn't normally come across that. Okay, so this is actually the ASCII for WHAT, what. Yeah, so pretending that our message had what in it and pretending that we hadn't already XOR'd the daylights out of it with add round key, you might come across this in AES Encryption. Okay, so I've written this out as a column just here. Whoa. Because in a matrix that we're going to see next time, this is actually going to be one of the columns, and this one just here is going to be one of the rows. Yeah, so I've written that out as a row. But the 57 is to be multiplied by the 2. The 68 is to be multiplied by the 3. Oh, they're hexadecimal too, so I suppose I should spell out the digits. The 61 in hex is to be multiplied by this one just here, and the 74 by this one. And like we said, if you multiply 61 by, well, we'll get to that eventually. Okay, so let's make a little bit of room, and let's go through this entire dot product and see what we get. Okay, so 57. First of all, let's figure out what 57 is, or 57 in hex, what it is in binary. Okay, so in binary, I've got a calculator here. I didn't work this out in my head. In binary, 57 is 0, 1, 0, 1, 0, 1, 1, 1. Okay, and we're multiplying that 57 for our dot product by 2. So multiplied by 2. Okay, well that's nice and easy. If we want to draw up the grid for that, the grid for our polynomial multiplication, what we've got in well, we've got in the first value, we've got x to the 6, and there's no x to the 5, but there's an x to the 4, then there's an x to the 2, and an x to the 1, and an x to the 0. Okay, so that is this first bit sequence written out as a polynomial, and the second one's really, really easy. It's just x to the 1. Okay, so if we draw out a little grid like we did before, we'll have 0, 1, 2, 4, 6, and just 1 is the only column that we've got. And then we just start adding together like we did before. 0 plus 1 gives us 1. I might just fix my little grid up. There we go. 1 plus 1 gives us a 2. 2 plus 1 gives us 3. 4 plus 1 gives us 5. And 6 plus 1 gives us 7. Okay, so if we convert this back into a bit sequence, we can see pretty clearly that there's only one of each of these values. So yeah, we'll put a 1 in the 7s column since 1 is an odd number. There's no 6s, so we'll put a 0 there. 0 is an even number. There's 1 5, so we'll put a 1 there in the 5 column. There's 0 4s, 0 is even, so we'll put a 0. There's 1 3, there's 1 2, and there's 1 1, so that's 1 1 1. And there's no zeros. Yeah, so 0 is an even number, we'll put a 0 there. This is the bit sequence that we end up with. 1 0 1 0 1 1 1 0. That doesn't sound right. Anyway, moving along. Oh yeah, no, that's right. I think that's right. I think that's right. So if we come back to our page over here, we've now got to reduce it modulo this value just here. So 8 4 3 1 0. I always forget this polynomial. I always forget it. All right, 8. There's no 7, there's no 6, there's no 5, there's a 4, there's a 3, there's a that, there's a that, and a that. Okay, so that's the polynomial that we have to reduce by again. But what you'll notice here, and this happens a lot, our value just here is actually smaller than the polynomial that we're reducing by. Our answer already fits into a byte. And in that case, well, we don't do anything. You don't perform any of that long division step that we saw before. Instead, you can just record this as your answer. Okay, so let's just write this at the top. 1 0 1 0 1 1 1 0. Alrighty, then we'll just scrap all this, and we've got to do the next product for our dot product. Let's go over to the slides and see what that is. Okay, so we've figured out the answer to 57 multiplied by 2, and now we've got to do 68 multiplied by 3. Once again, they're all Galois fields. I mean, 68 multiplied by 3 is not difficult to do, so let's see what it is as a Galois field. Let's grab my trusty calculator again, hex, and we've got 68 into binary. What have we got? 1 1 0 1. Alright, so it'll start with a 0 over the side. 0, 1, 1, 0, 1, 0, 0, 0. Okay, that's 6, 8 in hex as binary, and we've got to multiply that by 3, and 3 in binary is just 1, 1. Okay, so let's convert these to polynomials for the next step. Okay, so we've got a 1 in the 6th column, so that's x to the 6, then we got x to the 5. There's no 4, but there's x to the 3. And that's the first polynomial. And the next one is x to the 1 plus x to the 0. Okay, that's the second polynomial. Alright, so we'll write this out as a columns and as a grid, sorry. We've got 3, 5, and 6. 3, 5, and 6 in our first, and we've got 0 and 1 in our second. Alright, then we just start adding the exponents together. So 3, or x to the power of 3 times x to the power of 0 will give us 3. And we've got a 4 here, 5, and a 6, and a 7. Okay, so that's our exponents. After we multiply those two polynomials together, let's join them into a bit sequence. We've got 1, 7 just here, and 1 is obviously an odd number, so we'll put a 1 there. We've got 2 6s. 2 is an even number, so we'll put a 0 there. We've got 1, 5, so I'll put a 1 there. We've got 1, 4, put a 1 there. 1, 3, so I'll put a 1 there. There's no 2s, there's no 1s, and there's no 0s. So this is our resulting bit sequence, and I think, once again, this is probably, let me just write out that other polynomial, I'll see if I can remember it. So there's an 8, there's no 7s, no 6s, no 5s, there's a 4 and a 3. Yeah, it's bigger already. So our value, once again, is already less than the polynomial that we would normally reduce by. So once again, we don't have to do the reduction step. Instead, we can just write this in our answers. So this is 1, 0, 1, 1, 1, 0, 0, 0. I want to mention also that if we just take one of these values, say the first one just here, so let me just punch this into the calculator, punch it in, mind you. 10101110 equals, and hex. If I convert this value just here to hex, what I get is AE. Alrighty, so then if we come over, this would be how you check your answer. 5, 7 in the mul2 table. So we want to look up the mul2 table at the index of 5, 7. If we come over here, this is mul2 just here. 5, 7, so 0, 1, 2, 3, 4, 5, and 7. So 0, 1, 2, 3, 4, 5, 6, 7. Yeah, there you go. You see AE. That's the answer that we got. Yeah. And the other one, if we have a look at that too, just to make sure that it's correct, the other answer that we got was 1, 0, 1, 1, 1, 0, 0, 0. So you can check the answers that you're getting against what's in that table. This is B8 just here. This is B8. So let's have a look. So this should be row number 6, column number 8 of mul3. Let's have a go. So 6, 8. 1, or 0, I should say. 1, 2, 3, 4, 5, 6. Always start counting from 0. And what was the other one? 8. 0, 1, 2, 3, 4, 5, 6, 7, 8. Would you look at that? B8, which is the hex value for this. Okay, so we know we're onto the right track, but that's a good way to check if you're doing things right. Okay, but moving along, we're not quite finished our dot product yet. What we've got to do next is multiply the Galois field 6, 1 by the Galois field 1. Well, that's nice and easy because it stays exactly the same. So it stays as 6, 1. But we do need it in binary, so I'll just convert that. In binary, that becomes 1, 1, 0, 0, 0. A bit of 0 there, and then a couple of 1s, 1 and a 0. Oops. Nearly lost my mouse. All right, so that's 6-1 times 1, and the other one that we've got to do is 7-4 times 1. So 7-4 times 1 as Galois Fields is just going to give us 7-4 again. So if we type 7-4 in hex, convert it to binary, well, you've got to be a bit more than, 7-4 equals, and then, okay, sorry, I pushed the wrong number. All right, so the answer to 7-4 in hex to binary is 0, 1, 1, 1, 0, 1, 0, 0. Okay, that's good. So what are these things? Well, these things are the 4 results of the products of our dot product. So all we've got to do now to finish the demonstration is add them all together. But what's really cool for us is addition is just XOR. So just wipe that out and copy these over here a little bit. What we're really doing is just XORing all of these together. And if you've got a whole bunch of things to XOR, as we do here, what you can do is the same mod 2 trick as we were doing a minute ago. Every time there's an odd number of ones in one of these columns, you put a 1 in the answer. Every time there's an even number of ones, would mean that if you XORed all of these values, you would get a 0 in the end. Okay, so there's an odd number of ones right there. I put a 1 in the answer. There's an odd number right there. Here there's 2 ones, that's even, so I'll put a 0 there. There's 2 ones here, so that's a 0. 2 ones here, so that's a 0. 4 ones here, that's pretty cool, so that's a 0. 4's an even number. 2 ones here, that's a 0, and 2 ones here, so that's a 0. So we actually only got 2 ones on the end. Good stuff. And you'll be able to check that answer at the end as well. I know that that is the right answer because I actually knew that the answer that we were looking for was 3. Yeah. Anyway, usually we'll just use a lookup table. And next time we'll have a look at matrix multiplication. But I think that the set of steps that they invented to get to the values in this mul2 and mul3, it's very clever, it's amazingly interesting. And you really got to start asking, what is it about those steps that would make this algorithm difficult to reverse? What is it about those steps that's complicated and confusing and diffusing? It's interesting stuff. It's very, very interesting stuff. So that's really why I wanted to go into those steps in the detail that I did today, because I just find them interesting. But usually you'd use a lookup table to compute those values, and then just do some, well, your dot products are really easy. Just a couple of XORs with the values that you look up. I'll probably put a link to that page in the video description, that Wikipedia page, and I've got a Patreon and a Facebook, so if you like what I'm trying to do here, head over there to Patreon and become a patron of What's a Creel, or head over to Facebook and say hello. Most of all, have a really excellent day, and thanks for watching. See ya.